Hello viewers, welcome back to another section of my YouTube channel tutorial. In this video, I'm going to take you through First Law of Thermodynamics. Kindly watch the video to the end so that you understand every part of the video. Please, if this is the first time you are visiting this channel, kindly subscribe so that you get more content like this. So, the first law of thermodynamics. Before we delve into this, let's consider what we call a system. So a system, as used in thermodynamics, is any part of the universe which is under investigation. So if we take any part of the universe under investigation, we call that a system. A system can be simple as water in a test tube. So whatever system you are using for your experiment, that is the portion you are investigating, and we will be using it in thermodynamics a lot. So let's see. There is a property of a system, and this property is what we call energy. So energy is a property of every system. That is, every system will possess energy. Now this energy, as I'm talking about, changes, and the change in energy within a system has a value which is also equal to the difference between the net heat supplied. So I'm going to bring out parameters, that is the heat supplied. So the net heat supplied, which is represented by Q, minus the net work done. So that is going to be WNET. So we are going to have heat supplied to a system and the work done by the system as it changes state. When a system absorbs heat, there will be a change of state, and the work that will be done, when you subtract that from the heat supply, it gives us the total energy of the system. So mathematically, what I'm saying is delta Q minus delta W net is equal to our energy E. So the total energy, so the E is equal to the change in the heat supply minus the work done as the system changes in state. So this is the first formula I've shown you. Q net minus W net is equal to delta E, right? So let's see. For a closed system, generally, if you have a closed system will not have the matter being exchanged with its surrounding. So whenever you have a system will have a boundary. Then the boundary is going to set the system away from its surroundings. So when we are considering a closed system, the total energy E is equal to the internal energy represented by U plus the potential energy represented by KE, then plus the kinetic energy represented by KE, then plus the potential energy represented by PE. So this is the formula for the energy contained in a closed system. The internal energy plus the potential plus the kinetic. Now, to apply the first law of thermodynamics to this, let's see. The total energy here from our first equation is what? Delta Q net minus what? Delta W net. So this will be equal to the total internal energy plus the KE plus the PE. So first law of thermodynamics is saying that the total energy contained in a system remains constant. So once a heat is supplied, the work done by the heat, when you deduct it from the heat supplied, you get the net energy contained in that system. So obviously the total energy in a closed system is its internal energy plus the kinetic energy possessed by it, then plus the potential energy. So applying the Q net minus W net, you make it a subject here, and you get this new equation as I have here. And this is for a closed system. Now, for a closed system which is stationary, since we are talking about potential and kinetic energy, if your closed system is stationary, then our formula will have the delta Ke to be equal to 0. Then the delta P will also be equal to 0. For that reason, we have our Q net minus W net to be equal to the internal energy. So this equation, this is our third equation, is what we call the non-flow energy, equation, or NFEE. So non-flow energy equation. So I'm going to take you through an example I have so you understand what I am saying. So let's consider another aspect. So let's see. I have a problem here. So there is a problem. A gas trapped inside a piston cylinder device receives 20 kilojoules of heat while it expands, performing a boundary work of 5 kilojoules. At the same time, 10 kilojoules of electrical work is transferred into the system. Evaluate Q, that is the heat supplied, the work done, as well as the internal energy with appropriate signs, positive or negative. So our question has been summarized here. We have a piston cylinder device. We have a cylinder where a piston is being pushed, and this cylinder receives 20 kilojoules of heat. That is here, a heat. So this 20 kilojoules is supplied to the cylinder. So it expands upon heating, and it does a boundary work of 5 kilojoules. 5 kilojoules. Then at the same time, a 10 kilojoules electrical work is transferred into the system. So now we are supposed to find the total heat supplied, then you find the work done, as well as the total internal, or the change of internal energy, that is the change in internal energy. So how do you get these parameters being asked? So let's do our solution here. So let's see. The total heat supply, that is our Q in, is equal to positive 20 kilojoules. It is being supplied, so it's positive. Then it is doing a work. So the work done here towards the boundaries, that is the work out, is equal to positive 5 kilojoules. So when a system is doing a work, it is pushing it is pushing towards the boundaries, so it's a positive work. So let's see, this is the work done for the boundary, so let me make it WB. Then you have the next work done, which is the electrical work. So you can see that the electrical work is transferred into the system. So this is a negative work done on the system. The system will do the positive work by expansion, then there is a negative work done on it. So W E for the electrical aspect is equal to negative 10 kilojoules. So the problem is saying evaluate Q, that is the total energy or heat supplied. So our Q net, which is also equal to the Q, is also equal to Q in, because we had only a heat supply, and this is giving us positive 20 kilojoules. Now let's see the W net. The total work done is equal to the WB plus the WE, right? And this is positive 5 kilojoules plus negative 10 kilojoules. And this is going to give me negative 5 kilojoules. How do I find my internal energy delta U? I showed you the equation that in a closed system from the first law, the Q net minus W net is always equal to the change in internal energy. So now I have 20 kilojoules, which is positive, minus my W net, that is 5 kilojoules, and it's negative, should give me my delta U, right? So let's see. Let's take the unit out. So I'm going to get 20 plus 5, and that is equal to positive 25 kilojoules. So this is how we apply the first law to solve such a simple problem. So a recap: the first law, we considered a system which is a part of universe under investigation. A system has a boundary which is separate itself from the environment or the surroundings. Now, energy is a physical property of every system where when the heat supplied to a system, we subtract the net work done on the system by the change of state, then we get the total energy. So the first law of thermodynamics is saying that the total energy of a system remains constant. So if you take a closed system where we had the total energy to be the internal energy, kinetic energy, and the potential, we can apply the first law by bringing in the Q net minus W net equals this. Then we considered a stationary closed system where the potential and the kinetic is 0. So we had the non-flow energy equation where the Q net minus W net is equal to delta U. We solve this example here. Then now remember, this system that we have here is stationary system. That is why we use this equation here. Thank you for joining me in this video. Hope seeing you in my subsequent videos. Don't forget to like, subscribe, and share.